Hello, my dear students. I welcome you once again to our online lecture series. Today's topic is on the introduction to differential equations part 2, and I intend to cover the classification of differential equations by order and type and the application of differential equations and the likes. All right, let's delve deeper into the video.
Welcome to the video on Introduction to Differential Equations for Economics 2. I am Dr. Chingshubham Manimohan Singh, and I'll be guiding you through the fundamental concepts and applications of differential equations, particularly those relevant to economic modeling. Differential equations are essential mathematical tools, often describing how quantities change over time or space. Many economic models for population growth, market dynamics, and investment returns are expressed this way. Understanding them allows us to predict future behavior from current conditions. An ordinary differential equation, or ODE, involves derivatives with respect to only one independent variable, often time or distance. The order is determined by the highest derivative present. For example, $d(p)dt equals $kp) is a first-order ODE, modeling population P over time t. Differential equations are classified by order and by linearity and type. Order refers to the highest derivative, like first order or second order. Linearity depends on whether variables and derivatives are raised only to the first power. These classifications help determine the solution methods. The first of the four fundamental equations is exponential growth and decay, described by $dy/dt equals ky$. This model is used for bacteria reproduction, radioactive decay, and compound interest. The constant k determines the speed of growth or decay. The second pair of fundamental equations are second-order models, harmonic and hyperbolic motion. Harmonic motion, $d²y/dt² equals -k²y$, produces periodic, bounded solutions, modeling systems like pendulums. Hyperbolic motion, $d²y/dt² equals k²y$, produces unbounded solutions, growing exponentially in one direction. A general solution includes arbitrary constants, because infinitely many functions can satisfy the differential equation. A particular solution specifies exact values for these constants by using initial conditions, such as $y0 equals $5. This allows us to find the unique solution for a specific system. The order of a differential equation is determined by its highest derivative term. For instance, an equation with $d² x force dt caret $2 is at least second order. The order is important because it dictates the number of initial conditions needed to find a particular solution. To verify a proposed solution, substitute the function and its derivatives back into the original equation. If the left-hand side equals the right-hand side, the solution is verified. This systematic process ensures the mathematical validity of the proposed differential solution. Population growth models follow the differential equation $d(p)dt equals kp$. We can find a particular solution, $p of t equals ce caret kt$ by using initial conditions. For example, knowing a bacteria population starts at 100 and doubles in 10 seconds allows us to find C and K and then predict future population levels. Here are several practice problems demonstrating solution verification, finding general solutions, and applying initial conditions to find particular solutions. These examples illustrate the systematic methods required for solving various types of differential equations. We've covered classifying day, modeling real-world phenomena, applying initial conditions, verifying solutions, and solving population growth models. Reflect on how order impacts the number of required constants and the role of initial conditions in making specific predictions. Thank you for watching this video. As Galileo Galilei once said, mathematics is the language with which God has written the universe.